So let's say we place an object at some initial position, some mass, and let's say, since it's on a circular path there, that it happens to have some initial velocity. And what we want to do is describe its motion, or excuse me, describe its speed as a function of any position it may be at. So let's say it's now down here at some general angle theta, defined as we've shown, off the vertical. Defined off the vertical. So what we're interested in is describing this speed as a function of theta. Okay? So we have some length L here, and let's see if I can come over here and do this neatly. The distance the object has at this location down here, that vertical distance is going to be your L cosine theta. Right? L cosine theta down to this height. And initially, this was at this height, which would be L cosine of theta naught. Is that all right with everyone? Everything okay so far? So we're going to write the energy equation. So we have that the work done is equal to 1/2 mv squared minus 1/2 mv naught squared. And again, the work done by mg is going to be equal to mg downward, and travel distance being L cosine theta minus L cosine theta naught final position minus initial position. And you look at from your free body there, which isn't completely free because once again I forgot to write the tension here, which is not doing any work. Okay, now it feels better. And so notice that we have mg downward, and we have this travel distance minus the other shorter travel distance. So as long as this is greater than that, there's positive work done. This value being greater than that value, which fits with the picture. That's equal to our mass divided by 2 times v squared minus v naught squared. So once again, you can see the mass disappears. We could factor out the L over here. We could bring the 2 over. So we're going to have 2GL times the cosine theta minus cosine of theta naught equals v squared minus v naught squared. And then we would kick the v naught squared over and square root both sides. And so we end up with an expression for v, which is equal to the radical of 2GL, the difference in our cosine readings, plus the initial speed squared. So that's the speed at any theta. At any theta location. So if we happen to let theta be 0 degrees, at 0 degrees, this turns to 1. And I'd like to go ahead and look at that.
Should be maximum.
Excuse me?
Should be maximum.
Yeah, I would think. We should expect it. I mean, our gut feeling is, so let's double check the mathematics there. Excuse me? V at 0, this result is telling us that we get 2GL. Cosine of 0 is 1 minus cosine of theta naught plus the initial speed squared. So notice that let's say we could look at this in general as we have these values here, non-zero values say for these. But let's say that theta naught was pi over 2. Pi over 2 up here.
You lost your battery.
Oh, okay.
As quickly as possible here.
Didn't even know that. I didn't notice. I didn't stop moving or talking.
Good to work.
Okay. Is it working now? Okay, good. Okay. I don't know how long ago they lost it. So let's put theta naught up at the top here at 90 degrees.
It's not working.
All right.
You gotta switch it back on.
Make sure you get Randy on there. Thank you. Okay, we good now? Okay. So let's say that we put this up initially up there, like this, and let's say we give it 0 velocity. And so theta naught being pi over 2, then what that would do as this thing whips down here, and I want to check this down at the bottom with theta equals pi 0 down here. When it's at this location, what we'd get is we would drop that in here. So V at 0 with theta naught equals pi over 2 and V naught equaling 0, we're going to get the square root of cosine of pi over 2 is 0, V naught is 0, we get the square root of 2GL. The other thing you can notice, so that's something you may have seen in physics. Okay, the other thing you can notice here is that if you've given this thing some arbitrary position like we've done in the original problem with some initial velocity V naught, that notice that this difference right here, 1, if I'm talking about the motion down here at the very bottom, which is what we are doing by making this equal to 1, then this is always taking away from this value of 2GL. So if you've given this thing any position other than up here at pi over 2, some lesser value, then your speed is going to be, at the bottom, is going to be something less than that radical 2GL. What if you had placed this up higher on a non-compression type of element? I mean, or something that can't carry, that can carry compression. So you have the arm up here above, where theta naught is greater than. The cosine of that obtuse angle is negative, right? And so then these become additive, which you would expect, giving you a higher speed when you get down here to the bottom. Okay, so that's the kind of thing that I want to encourage you. I've mentioned this before. Generalizing, do a problem specifically like we did, and then you can take and fairly easily oftentimes generalize it, and then you have a governing kind of an equation to describe this motion in general. Okay, any questions on that? Okay, now before we start talking about potential energy, why don't we see if you have any pressing questions from previous homework, since we have an exam coming up. Anybody have anything pressing? I might be able to get you on the right track. Oh, gee, Ian's going through a whole bunch of pages there.
I just came to the last three problems in the last chapter. How about we look at 48? Number 48, page 139. For either or one. So.
Okay, 48 on 139.
I've got part of it. I just can't get another part.
Okay, that's this guy. I drew myself, well, let's see, here's the whole problem.
See, I can get the m divided by 2y times root b squared plus y squared multiplied by g, but I get plus a. And I'm trying to solve for the plus a part, and I can't get the b squared or divided by 4y cubed.
What's the A?
The a represents the overall acceleration of the mass, which I assumed I could find based off of the I can't remember the name of it, constrained motion of the cable.
Mm-hmm.
And my equations do not work out.
Okay. What I did, well, the trouble with this is that it'll take time to fiddle with it. Maybe I don't want to take the class time on it. Maybe we can. Anybody else gotten that problem?
Yeah.
You did?
You got it?
Yeah.
I'd love to see it.
Okay. Why don't we approach it that way? See Jake.
Yes.
And if other people haven't gotten it yet? How many haven't tried it yet? Be honest. Okay, good. You got a weekend ahead of you. So, okay. There's no classes tomorrow, so that'll be nice. So keep in mind that we've got something spooling up here on the drum, and you can tackle it kind of the way that I described previously. What I wrote down here in the book wasn't recently, but I called this L right here, and so that's going to relate to B and Y right there through a Pythagorean relationship. And then I went ahead and tucked in here something I called S, the amount on the drum. We could get at that by calling the length of the cable allowable change on that, like I talked about in a previous session. So what I did is I put that part that's on the drum over here, called it S. So if I differentiated that, this length of cable was fixed the way I have it written here. And so, oh, I'm underneath, sorry. So I'd get, and I hope that shows up on the DVD, the derivative of this fixed length of overall cable, including what is spooled on the drum, is fixed. So the derivative of that length is 0. The derivative of this is the 2L dot plus an S dot. And the derivative of the constant part disappears. The part on between the tangencies on the pulleys. So you get this relationship, and this S dot happens to be what?
V.
That's going to be the defined V value. You were probably okay with that?
Oh yeah, absolutely. It's the next step, finding the acceleration.
Okay. And then that cable's moving, is that moving at a constant?
Yes, it was given as a
Constant speed. So then that means the derivative on that is 2L double dot plus S double dot, which zeroes out, equals 0, which means that L double dot must be 0. Does that agree with your work?
I know I could get that, but it doesn't seem to make sense.
Anybody else that,
Yeah.
you got that?
Yeah.
Okay. So what that tells us then is that the acceleration of this diagonal section of cable on either side is 0, is what this tells us. Okay. Now, you then draw your free body diagram, as I did over here, and write, I'm going to actually go ahead and play with this with you a little bit on the board here, because I think there might be something useful there. Here's the geometry. Here's the mass hanging. We have a tension, symmetric tension values because of frictionless pulley condition here. And then we have the geometry of this cable symmetric to both sides. And that's what I want to point out to you. So we have distance y, we have horizontal distance b for the overall cable length, and then this is then the radical of y squared plus b squared. Okay? When I start writing F equals ma, the equations of motion here for this, if I did you use a traditional x and y? Or actually, y was defined downward, wasn't it?
Yes.
Okay, so I'm going to go ahead and use y downward. I'll use x to the right. Okay, so I'll stick with this coordinate system then. So then if we write sum of forces, sum of forces x must equal mass times acceleration x. We know that, does this body accelerate to the left or right? No, because of the frictionless pulley, this thing remains in vertical motion, doesn't it? So we could make mention of that. Motion remains vertical. And so then summing forces in the x direction, this motion remains vertical implies that AX is 0. So we have a static condition horizontally. And so instead of writing T cosine some angle here, what I want to...
2TB over L.
Excuse me?
2TB over L using the lengths you defined as a
Yeah.
triangle.
Yeah, I want you folks to get in the habit of using direction cosines off of the geometric relationships you see here, instead of writing down some angle and then fiddling with your calculator or whatever on it. So that's the reason I wanted to show you this.
Y over L, yeah, you're right.
So we have T to the this force component to the left, T times the cosine of this angle. Well, you look up here, the cosine of this angle is B divided by that, isn't it? B divided by the radical. And then the other force is to the right, plus T times the same angle equals 0. And you can see that thing just zeroes out, right? Doesn't mean the tension's 0, obviously, but the whole thing just degenerates. If you change that and write the forces vertical, that's where you get your dynamic motion. Sum of forces vertical. So sum of forces y equals mass times acceleration y. Now what is acceleration y? With y defined positive downward. That's y double dot, isn't it? Y double dot. So this becomes y double dot, and then our sum of forces y again is going to be upward in both cases. So we're going to have two of those components, and they're made up of T times the sine of this angle, which happens to be, as you mentioned, y divided by the radical. Is that right? And that's equal to m y double dot.
Yeah, why is it not negative?
Because y was defined in the book, in the problem in the book, as pointing downward.
And so is it
And
the
so I'm sorry. Thank you. Good catch.
Don't you need your weight too?
Oh, thank you. Forgot that too. Okay. Let's retract all this. So we have this. This is upward. This should be defined as negative. So we have a negative on this term. And then we have mg in the direction of y. Thank you for catching that. Something would have shown up real soon if I hadn't put that in there. Okay. And then the kinematic relationship we had from the cable spooling on the drum, right, is going to give us a relationship to put into here, which is what? Oh, actually, no, not into there, I guess. No.
Y is going to be half the drum speed.
So what I'm going to do is I'm going to come up and erase the x stuff because the x stuff was just equally balanced, right? I don't need that. So let's talk about that for a second. So we have this equation. Now, what kinematics did we have from the cable length? What did that tell us?
That's Y double dot with 0. Triple dot.
And we're supposed to write the result in terms of what? We're supposed to find the tension, determine the tension in the cable in terms of the y-coordinate of the cylinder and the given downward velocity v. Okay, whoops, I better move this down here. Let me move that down a little further. So if we look at our equation, does that agree with what you had, Jake?
Yeah.
Okay. So what's our next step is the question to ponder. Don't help us yet. Had you gotten that far with it, Ian? Got that? Okay. We don't have anything in there that has the velocity of that drum, of the cable being pulled, do we?